Welcome to After Hours Engineering, episode 19. In the previous episode, we built a SPI slave and UART and then synthesized them directly onto our BlackiceEdge. These protocols gave us an opportunity and a way to communicate with our FPGA. And in this episode, we are finally going to synthesize our RISC-V processor, the Ranger RISC. And we're going to use UART as a way to interact with the processor via a custom top module. So let's go! Remember way back when how we used LEDs to view signal states on the A09? Well, we're going to up our game and instead pipe those signals via UART back to our computer terminal. So let's start with the control matrix. The idea here is to expose as many signals as we can up to our top module so that the top module can route them out to the client, which is a Go program. So the only real changes we've made between simulation and synthesis was to add this additional signals right here, these output signals. Once these are exposed, we can then come to the RISC-V processor and pick up those additional signals, which we'll scroll down here to the control matrix. We can pick them up and add them to the RISC-V processor's additional signals, and then route all of that out and up to the top module. So if we come up here to the top module, we can see in our definitions area right here, we've grabbed all of those outputs and we've captured them here. You normally wouldn't do this. This is just for our test harness. And by doing this, we have increased the resource unit by well over 2.5 times. We're probably talking, when you look at the output of the toolchain, it's going to say 2,500 LUTs. The processor itself, all by itself, is about 1,200 or 1,300 LUTs, which is still actually pretty big for a RISC-V processor. But in this case, I understand because we're going to be looking at all of these signals here. So if we scroll down to our top module, we can see that it is built out of a bunch of states, a whole bunch of extra states, and they're over here. Now these states normally wouldn't be in any kind of top module. They're here merely to support our test harness. You might have something like resets of the CPU, but you certainly wouldn't have any of these signals right here. So we'll start off in the idle state. This is our top module and it wants to idle when it comes up. So I'll collapse these sections right here. And here's the idle state. And what it does is it waits for a byte to come in from the client. And again, the client is a Go program, and I'll cover that in a moment. And what it does is it looks for different signals, or bytes in this case, coming in from the client to say what to do. And the two most important ones are the reset, which allows us to send a signal to the processor to reset itself, or in order to send back a 50 bytes, a pretty large chunk of data, back to the client so that we can see what the processor is doing. That was the intent of exposing all of these signals so that we could actually see what the processor is actually doing. And that's what the idle does. Now once it recognizes a command like the reset, so if we come up here to the reset, right up here, we can see that it goes through a sequence of events. One, it drops the reset pin or signal low so that the processor sees it. And it does this for an arbitrary number of clock ticks. In this case, I've set it up for 16. So it'll hold the reset low for 16 clock cycles and then finally raise it high right here. And that's what the reset does. The second most important signal that we're going to look at is the S. So let's come up here and take a look at the request. And what it does is it resets our counter. This is a counter that's going to count the number of bytes that we're going to send back to the client. And this is the largest section. It's gigantic. So we start off at 0 and we're going to send back the matrix state, the vector state. Then that'll take up one whole byte. We'll send that one. Then we'll collect up the rest of the vector state and the interrupt instructions state and bottle those up and send it back as a byte. Then we'll go ahead and grab a bunch of signals from the control matrix that is, toggling the little signals on all of our little components. And we'll bottle that up into a byte and send it back. And from there on out, we'll start grabbing full-size registers, all 32 bits, and sending them one byte at a time. And 32 bits is obviously 4 bytes. So we'll send out 4 more bytes. We'll send out the instruction register byte, the PC prior value, AMUX, BMUX, and all of these values. And then as I was doing this, I was adding more signals on. So I decided I wanted to add in a bunch more of the control matrix signals, and including the take branch. And then I sent out a bunch more registers, data out. Then I sent out another bunch of clocks. In this case, I'm only sending 1 bit, but I'm sending a byte, so I set the rest of them to 0. And then finally, I send out 2 more registers, the ALU and the MDR. And in total, that's 49 bytes we're going to send back. Now, we're sending that at 115 baud, so it'll go pretty fast. It'll send it almost in the blink of an eye back to the client. And the client's job will be to display that, and we'll take a look at that in a minute. And then once it's done sending it, it then goes back to idle. It detects that last byte that we sent count and switches us back to idle, starting the whole cycle over again, waiting for commands. That's how the top module works, and it consumes an overwhelmingly large portion of our LUT count. But that's okay, it's just a test harness, and I wanted to show a different way of exposing the CPU signals rather than a bunch of blinking lights, which we all love blinking lights, but this is just way too much information to try to put into a bunch of LEDs. And finally, at a high level, let's take a look at what the top module actually is. It's built out of all the components that we've been covering throughout the series. Starting at the most important one is the range of RISC processor, our RISC-V processor. And we have our 7 segments display that will display the command coming in. We have our parallel port register, which is 8 bits wide, and this is the one that has been mapped in the address 800 hex range. Then we have our 2 UARTs for transmitting and receiving from our client. And altogether, this is the top module. Now let's look at the other half of our test harness, the Go program. It's really simple. It doesn't do much other than just simply talk to the USB serial port and responds to it. It sends a byte and receives many bytes back. As in any Go program, there is a library out there called Serial that we can utilize, and I've set it up for 115K baud, not a problem, and I've attached it to the USB 0 port. We built a Go channel to read the input strings. This is supposed to set up non-blocking, but it doesn't really work, but I left it as it is. When we type a character and we hit carriage return, it sends that character through the channel, and on this side of the channel, we read it into a variable called standard in. Once we grab it, we turn around, and if it's not the letter S, then we just send that command all the way to the FPGA, wait for it to come back, and then turn around and literally send the S command right after it. So basically, anything we do, we're going to send the command, the FPGA will do something, then we'll set the S command, and we'll get a whole bunch of data coming back. And that happens in our show data section. That's this section right here where it's showing all of the data that came back via the UART and pulls them out of their buffers and prints them out using all kinds of wacky, crazy conversion routines to show them. And one of them is showing all the control signals that we got back here and any of the state or main top module SOC signals right here. And that's it. That's what our Go program does. Before we actually run that test harness that I just showed, let's step back and take a look at some of the issues I ran into as I was migrating from simulation to synthesis. And the first one was forgetting that simulation will probably do anything I want it to as long as the resource is available, and my desktop has plenty of resources. And in this case, I was asking it to do 8K words, which if you multiply that out, is more bytes than the FPGA actually has in and of itself. So I had to go back to my definitions file and drop this down to just 1K words. And once I did that, Toolchain stopped throwing an error saying you've overallocated your block RAM. Next, I want to talk about a specific error I was getting called event signal conflicts. On the left here, we have the original code in our synchronous block. The problem was that this was fine in simulation, but synthesis didn't like it at all, and it makes sense. This signal, the IRQ hold pending signal, is actually in two different places, but is dependent on two different types of signals right here. And synthesis flagged this immediately, saying that you can't do this. And it makes sense. I've got this flag trying to change based on two separate different flags, and it's hard to synthesize something like that. So in the end, I went back to the control matrix, and I also renamed the signals because I didn't like the way they sounded and begun with. It's still a 1-bit FIFO, but it no longer is dependent on two separate different signals, as you see over here on the left. It's a single signal, a reset signal. And that corrected this particular error. This actually synthesized correctly. It took me a while to figure this out, but eventually, with a bit of Googling, I was able to see what the problem was. And so I reduced it down to a single signal. The next issue, which really isn't an issue, and it is something I kind of known about, but I forgot because I hadn't done synthesis in a while, and that is if you don't take any of your components and route them to somewhere out in the physical world, your toolchain has a really strong chance of logically reducing all of your components to zero. And so even though it synthesized it, which is nothing more than just syntactically and structurally checking your code, nothing comes out. Your resource allocation will be almost zero. And as soon as I took one of the components in my design here, the RISC-V CPU, and routed it to one of the other components, or pins, or outputs in this case, suddenly all of these issues, some of which I've already covered, and I'm going to cover others in a second, started showing up. And so that's something to consider and I would like to ask if anyone knows, can you actually synthesize something that goes nowhere? Next is a bit of refactoring. I wanted to narrow the execution stage of the processor, the state, and so I decided to move a lot of the combinational portions of that circuit out and up into the top level. And two of the bigger ones was detecting whether what ALU operation it was, which you can do separate and in parallel. And the other parallel operation was determining whether to take a branch. Granted, this doesn't do so well for power optimization because all of these circuits are constantly operating. In a proper design, you would want to use either clock enables or power gating to control whether you need to run extra circuits. But I kind of threw that out the window, and I'm using a lot more parallelism. Next, I'd like to talk about device utilization. And in this case, we can see here that we've used a considerable amount of resources in terms of LUTs, but this is almost exclusively, at least 50% of it, is the implementation of the top module and all of the support circuitry needed to talk to the client, the UART, the 7-segment displays, everything. The processor itself is probably right around 1100 LUTs, so it's still kind of big, but still this is overwhelmingly everything about the test harness. It's not so much about the RISC-V processor itself. Here we have our block RAM. Now, remember I said that I was a little bit overzealous with how much memory I wanted during simulation. When I had synthesized, I went over I was at 120%. So I forget the simulation can give you anything you want just about. And so I dropped it down to 1K words. And then on the I/O side, we have 23 pins being used, which is exactly correct, because if we come back over to the top module up here, we see that if we count all of our inputs and outputs, we can see that's how many, 12 plus 6 plus 1, 2, 3, 4, 5, and if we add them all up, that comes out to exactly 23. The final thing I'd like to talk about for device utilization is this global buffers area right here. And here our toolchain is determined that I need to use 6 out of the 8 available. In order to see which ones those are, I'll bring up this diagram right here, and I'll scroll to the top until we see this section right here. This is the spec sheets, one of the spec sheets for the FPGA. And as you can see, we have 8 of them available depending on which one. There's 8 no matter which variety you have. And the toolchain is determined that my clock is driving quite a lot of components all over the FPGA in order to meet some minimum timing requirement. So if I hide this again, you can see that my minimum retirement requirement I asked for was 18 megahertz. And so in order to perform that, it needs to use some of these buffers right here. Now these buffers are high drive, low skew, and the key here is low skew, because you ultimately want all of your components with as close as you can into the same clock domain. If there's a significant amount of skew, technically any kind of skew, you've entered into a new clock domain. But for our purposes, at a lower frequency, that gray area between domains can overlap a bit. And in this case, it's determined that it needs 6 of these buffers, low skew buffers, to distribute my clock. So now we'll go back to the program and take a look at the program. And here's my clock. If we scroll to the top, I'm using this clock. And so I'll scroll down to the section where I'm actually taking the clock and I'm bumping up a counter. This counter is used up top here, right here, to generate a CPU clock signal. And so I'm either going to use a manually running clock via that counter, it gets routed into here, or I'm using a manual clock. If I'm using the run clock, that CPU clock is routed into my processor, which gets routed to registers, register files, instruction register, memory, you name it. There's at least a dozen or more components in there, and they all need to get their clock at pretty much as close as possible at the same time. Because if they don't, then you'll start running into anomalies as you're running, or you'll have to lower your frequency to the point where you're almost at a standstill. But in this case, we can drop down to about 18 megahertz. And that's what I wanted to talk about. So the toolchain is determined that in order to distribute this clock appropriately to all the devices, it's going to need to use 6 of these low skew devices right here to distribute the clock as best as it can. And that's all I wanted to talk about in terms of the global buffers, why 6 of them were used. Now I've glossed over it quite a bit. It's significantly more complex than that. It's more than just about the clock skew. It's also about the drive. These buffers are also high drive buffers. But if you look at the specs, you'll definitely see that all global buffers optionally drive all clock inputs. And that's exactly what is happening. It also supports clock enables, which is helpful in other scenarios. So if we bring up the SBG, you can see that in the other spec, this is exactly what that device is for. So the next thing I want to talk about is the examples and our memory mapped I/O so that we can get started on the test harness. For memory map I/O, I've chosen to make it very, very simple, where we split memory up into 2 halves. The lower half from 0 to 7F holds the BRAM, and 800 is considered the memory mapped I/O. Both signals, memory write and I/O write, are active low. So for memory write, in order to bring this low, this value here needs to be a 0, but this value also needs to be a 0. If it's a 1, we're not doing any kind of writing whatsoever. And for I/O write, we look at the very same bit, the 12th bit up here, and we check to see whether it is a 0 or a 1. If it's a 1, which means we're writing to I/O, then we invert it, and that activates the I/O write signal. So if we come over here to our top module, we have our register defined, and it is the output port. I call it the parallel port in this case, and we're looking to see if we're doing an I/O write and we write the data in. The register out has been routed to the blade itself. So if I come down here to the blade, you can see that our register, our parallel, is wired up to the blade. So it'll always show what the last written value is on the blade, and it only shows the last 6 bits because the blade only has 6 leads on it. So that's the simple arrangement of the memory mapped I/O. It's broken into 2 halves. Finally, let's take a look at the 2 examples that we're going to run on our FPGA, our assembly code, if you will. In this case, on the left side, I've got a simple Cylon effect. It's a single pixel that'll move back and forth. In order to make that work, we need to load registers with certain values. So the very first line here goes out and gets the base address of the data itself, which is down here. And we'll look at the output for this. And then we start loading in all of our registers that control how the start pattern, when it detects the end of a pattern and switches back and forth. Also, we need the address of the I/O map In this case, it's a 800, which I've set down here. So this is 0, 1, 2, and 3. So data plus 3 will give us the 800 and load that into x6. Fairly simple. It's doing shifts of x3 based on x2, and x2 has been loaded with 1. So it's going to shift 1 pixel at a time left, and then it will store that in the I/O port based on x6, and then it'll check to see whether it's reached the end of the pattern. It's going to compare it to x5, and x5 was loaded with this value right here. If it is, then we simply drop right down into the shift right, so we start moving the pixel in the other direction, and of course writing it out to our port so that we can see the pixel move on our blade, and we check, and if we finish that pattern, we jump back up here and we'll go back and forth. That's what this does. The other example we have is considerably easier, and we'll run that one first, is that we're just simply going to count up to some value defined in this memory location right here. Again, we need our base address of the I/O so that we can store it to the parallel port, which is connected to the blade. And we will count up to that particular value and then stop. So the rubber has finally hit the road, and we're ready to synthesize our CPU. In order to do this, we're going to need 3 terminals. The first terminal is the assembler that will run, and that'll generate this output right here, which I've already run the assembler. Didn't take much. The second terminal is the actual makefile, and in this case I'm going to run it right now, and it's already uploaded. I'll let it run while we're doing this, but it actually takes a little while, about 30 seconds to 45 seconds to route and place it onto the FPGA. There it's finished, and now it's running the next PNR, the routing, which takes the longest portion of the time. So it's going to town, and while it's doing that, we'll come over here, and this is the terminal that will run our Go program, in other words, the client. And I'll start it up here, and it's talking, but now the code has not finished yet. It's still placing and routing. We'll give it a few seconds. There it is. It's finished, and you can see on the display it's all gone. The 7-segment display has gone all to zeros, and so now this code has been baked into the processor, into the memory. That's the way we're doing this whole process. So we can see what we're going to look for is this instruction. But before we do that, let's take a look at the reset sequence. So I'll bring up the code right here, and I'll come over here, and I've run the command, and I'm going to hit S, and it'll show us what state we're in. You can see that we are in the reset state. So this code right here is where we're sitting, sync 0. And in this case, we know we're just going to wait until the reset comes in, and we know the reset will come in. It's already actually come in. So if we just clock, it's going to move to vector 0. And so we should see in vector 0 that the PC load flag has gone low. So if we come over here and look for PC load right here, we can see sure enough that it has gone low. We can also see that we're manually clocking, which is fine. The processor hasn't halted, and neither are we ready yet. We don't go ready until we reach the last portion of the reset sequence. We've seen all this before in the simulation. We're just now seeing it on the real hardware itself. So now let's clock the thing one more time, and we'll go to vector 1. So if we come down here to vector 1, we can see that the memory read has now gone low. So let's check that. Let's find memory read. Right here it is, and sure enough, it's gone low. Great. So we're clocking right along here. So we'll hit the key return one more time. Now we're in vector 2. So it's going through the vector sequence. This is actually going and working on the hardware right now. The FPGA is routing all of the data back to them in real time over to our desktop here. So in this case, we should see now the PC load has gone low again, and it has. It was 1 on the previous one. If we scroll up, we can see that it was a 1. That's what's nice about doing it in the terminal, is I can scroll up and see what the previous flag values were. If I scroll back down, you can see that it's now low. Excellent. And we know that our PC source has been set to reset address. Excellent. And if we look at the data, we can see that there are various values out here, but they don't have a lot of value until we start getting into the main section of the program. So I'll hit return again, and we'll go to vector straight 3. And if we come down here, we'll know that the ready flag should have gone high. And sure enough, it is now high, because if I scroll up, you can see that it was low. So now it's gone high. So far the processor is doing exactly what it should be doing. We know that reset is complete. Memory read has gone back low again. So if we come over here and it's down low, and it's going to do that because we're going to go to the prefetch sequence. Now the prefetch sequence is currently doing nothing. There's a little secret I didn't tell you, and that is that I pulled the CSRs out for right now so that I could do that in a separate episode. Right now we're just looking at the core functionality of the processor, and so memory read will continue to stay low once we go to the fetch state. So I'll clock it one more time, and there we are. We're in fetch. Now the vector state will stay on 3. It never changes after this. It'll just stay there forever. But memory read is still low right here. Excellent. And at that point we're going to go up to the fetch sequence. So if we scroll right here to the fetch sequence, we know that our next state is going to continue to stay fetch, and we should see the instruction register load. So let's look at the instruction register first, and it is currently not loading. So we'll hit the clock one more time, and sure enough, instruction register loading. We're now actually loading an instruction, and voila, there it is. So if I come back over to our code and hide this, you can see there's our first instruction right there. So it is successfully loaded in our code. Now I'm not going to show the rest of the HDL while we're stepping through this. We're just going to focus on the assembly code, the machine code itself, while we step through this. So I'll clock it again, and now we're going into the decode state. So we're going to bump up the PC value right here. So if we look at the PC register, we're going to see that it bumped up to 4. Excellent. And if we keep going, we're now in execute state. So here is where we're now going to execute the state. And what are we going to execute? It's a load instruction. So this instruction register is set to load. So if I hit clock one more time, we're now in the load. I will bring up the source code again. We'll go down to the execute. We'll scroll all the way down to the load state. So we'll bring that up, and we'll take a look at the ALU load. Let's see what that is right now. Right there it is. So we have we're past that. We're now in the ID mem. So memread would be low, and it is. So we are actually executing the instruction, the load instruction, and we're going to load what the immediate is telling us to load. So technically we should load in the value 40 into the register, and that's eventually what we'll see. So I'll step through here. We'll go to MDR, which is right here. We're now at MDR, so we're memory reading, and sure enough, here's the MDR. This is the output from memory, and it is 40. We've reached into memory, so I'll hide this again, and we've reached into memory and pulled out the address for the data right here. There's the value that's in that slot right there. Excellent. So this instruction is executing just right, and now we're in the complete stage, which tells us to set our WS source. Let's take a look at it. There it is. It's set. Excellent. And now we're going to go back. We finished the instruction, and we're now ready to head back to the prefetch state. So there we are. We just executed our very first instruction. Excellent. This is exactly what it is. Now I'm going to go ahead and step a few more times, and we'll watch it move through these instructions right here. So let's go. So we should see it fetching, decoding, and let's take a look. There's the instruction 213 or right there. So this is the add immediate. So if we look at the output of our register, we'll see what we loaded. So we'll continue moving through there. There it is. That add immediate exposed a value. That's what's interesting about no-ops. In my design, I can use specific variants of a no-op to see what I stored in the registry file, because I can't expose the registry file or memory. It's too complicated, and I would have had to add too many structures into the code, making it even bigger and more complex. But there's a way around that using no-ops, and there's a whole variety of no-ops. In this particular case, I'm adding 0 to x4 and then doing nothing with it. But the great thing about it is that it has exposed it as data on the output of one of our muxes, and here it is. So I know that the load instruction actually worked correctly because it loaded X4 with 40, and we just exposed it. Excellent. That's what the no-ops are actually seeing. So you'll see a bunch of them in here. They were added only for the PC client. So we'll keep stepping through. There we are. We're now on the next instruction. This is a real instruction that we're actually adding to it. This particular one clears out the register. So we'll continue going through. It's fetching the next instruction. There it is, 2083. So we're going right along. We're going to load X1 with it. We're going to continue. We're going to go to the next instruction. There it is, 4203. Yep, excellent. So this is working. So far, it's working pretty good. And eventually, I'm going to keep going until we can get down to 20. We're right here, 2803. That's what we got right here. So we'll keep going till now we're at 210B. We're right here on this instruction right there. Keep going. We're executing away. Now we're at 183. That's the add immediate. Another no-op to expose the X3 register to us so we can watch it actually count in this case. And now we're going to move on to, this is the very first instruction. This is an important instruction. We're going to activate the IO write sequence here, signal. So you'll notice that it's a 0 right now. So as soon as we start executing that, fetch it, we fetched it. But now we're going to decode. It's still high, so we're not writing yet. We're still going, and now we're executing. We just wrote the value that was in that counter out there. We'll go one more, and there it is. You see the little LED on the pane up there? I'll highlight it with the little arrow. You can see that it's actually stored the value 1. We incremented from 0 to 1, and we stored it in the output register. So in this particular case, I can actually start the program running. It looks, I'll step through it a little bit more. We're going to continue to go through and watch just above the 073, you'll see the little LED. It's counting. And there you go. So let me switch over to the real clock, and you can see I've started the clock up. So now the program is actually running on the 48 Hertz clock. And you can see that it's counting up. So there you go. This is our very first program that we're running, and we can step through and watch the processor run on the real hardware without a lot of blinking lights, of course. Run. Excellent. Finally, let's go ahead and run that left-right Cylon program. We're not going to step through it in great detail. We're just going to watch it run, maybe take a look at a few variables here and there, but for the most part, we're just going to watch it run. So the first thing we need to do is assemble it. You can see I'll reload it here, and there it is. It's been loaded in. And then we're ready to run the makefile. So let's get that started while we're chit-chatting. So we'll come over here, and we will launch the program. There we go. We can't type any commands right now because the FPGA is going to answer under the old bit stream that's on there, but as soon as it gets to the point where it's uploading, it'll wipe it out. So let's give it a second while it's doing that. By the way, I noticed that one of the LEDs on the blade was not lit, and the blade needs to be inserted correctly to make all of the LEDs come on. So there it goes. It's uploaded. It's ready to go. And we're ready to talk to the FPGA. Okay, so there it is. And at least the first instruction is going to be the 502, so we can just start clocking until that starts showing up. There it is. It showed right up. That's it. Now I'm not going to step through this. I'm just going to hit the K key, which activates the clock and lets the program run on at full speed. There it goes. You can see the Cylon program moving the LED backs and forth. And there you go. It's running this program right here. And that's it. We have successfully synthesized our RISC-V processor onto an FPGA, and we have run programs via our assembler and embedded into the actual memory process itself. Plus, it is actually writing to I/O a separate register outside of the RISC-V processor. So we're well on our way to starting in the next phases of the series. Excellent. We have successfully synthesized our RISC-V processor, the Ranger RISC. However, we did so at a horrifically low frequency of 48 Hz. Now, as reported by the next PNR tool, we can actually synthesize at 18 MHz. The problem is our core clock is 25 MHz. Hence, in the next episode, we're going to look at phase lock loops, or PLLs, and maybe we might interface to a SPI device. You never know. So until next time, peace. I got a new chair.